Welcome back to Differential Calculus. In this video, I want to talk about rates of change. In order to do that, I'm on completely the wrong screen. Let me jump over to Desmos here. And when I'm talking about a rate of change, what I really want to do is generalize the idea of the slope of a line. For some reason, the tool that is pulling this into the video is losing the point a little bit, so I apologize for that. But you can almost see there's a circle here and here giving us the location of 2 points on the blue curve. When I click on it, you can see it a lot more clearly. Right? So, given a positioning of these 2 points, we can draw the line through those points, and we can talk about the rate of change of the function as being the slope of the line. Let's go back to my notepad and do just that. So consider, for example, a function f of x equals x squared plus 2x plus 5. And I might want to determine the rate of change between when x is equal to 1 and when x is equal to 3. This is a fairly straightforward function. I can evaluate that f of 1 is 8 and that f of 3 is, let's see, that'll be 9 plus 6 is 15 plus 5 is 20. So there's our 2 points. 1, 8, 3, 20. And if we calculate the slope of the line connecting those points, that is what we mean by the rate of change of this function over that interval of values. Application-wise, there's several different ways that you might be interested in rate of change. For most students taking calculus, the most obvious idea here is, in physics, the idea of velocity. A velocity or speed of an object is the rate of change of its location with respect to time. And so thinking about if you have a formula that specifies the position of the object, you can use this technique to figure out the speed of the object over the period of time. We're going to be looking at some things that are related to that and some things that are very much not related to that. There are a couple of classic examples that are used in calculus that aren't really all that applicable to anything, but are relatively easy to work with. One common one is a ladder. If you have a ladder leaning on the side of the building, you can think about the speed at which you pull the bottom of the ladder away from the building, and then as you're pulling the bottom of the ladder away from the building, the top of the ladder is going to fall down. That's a concept known as a related rates problem, because you're going to relate the rate at which you are pulling the bottom of the ladder away to the rate at which the top of the ladder is sliding down the side of the building. We might also think about the rate at which a sink is draining from a slightly clogged hole, or the rate at which a reservoir is being drained by a pump. Those are a couple of other very basic examples that we're going to spend a lot of time with because they are so basic. Population growth, if you are more interested in the environmental sciences. You might be more interested in economics and finance, in which case you will be looking at the rate of change of the relative value of one currency with another, or the rate of change of the value of a particular stock. All interesting things that we can think about. If I jump back to my graph, the last thing that I want to look at right now is the idea of the fit of the rate of change curve. You can see here that if we are looking in the general vicinity of x equals 0, the pink curve does a decent job, but not a fantastic job, of following the blue curve. If I move the points that I'm studying further apart, the fit gets a lot worse, and it can get pretty terrible pretty quickly. But if I move those points close to x equals 0, the fit gets pretty good. And in fact, I have to zoom in quite a bit to see any difference at all. And if I move these points even closer to 0, it gets even better. And I can keep zooming in. Eventually, I will get to the point where you can tell that there's a difference. If I bring those points even closer together and I zoom in again, you still can't tell. The difference here that I want to think about is an average rate of change as compared to an instantaneous rate of change. When you're looking over a large interval, you're going to be looking at what we call the average rate of change. It is on average over the course of the entire interval. If I zoom back out on my figure here, if I'm looking at a large enough interval, I might be looking at where, one of these days I'm going to learn how to do this. I might be looking at where the function is decreasing, and then it is increasing, and then it starts decreasing again. So that change between increasing and decreasing and increasing and decreasing will level out a little bit. And that's how you end up with a curve here for the average rate of change that is shallower than at any one point. That's an algebra level skill. This is something that you may have done, but may not have done in a course called college algebra, pre-calculus, whatever it may have been called wherever you took it. We want to do better than that. And so our goal is going to be to find a way to find the rate of change instantaneously at exactly the point x equals 0. That's something we'll play around with in a future video. For now, let me end with just something related to this for you to try on your own. Calculate the speed of a ball, and I guess technically I should say the average speed of a ball on the interval from t equals 0 to t equals 5. I didn't necessarily need to say the average because if we're talking on an interval that implies average, if its position is given by the function f of t equals 64 plus 4t minus 16t squared. This being math class, we don't really need to worry about units too much. But if you are the physically inclined, you are more inclined to think about things in terms of real world. You can certainly talk about t being measured in seconds and the position f of t being measured in feet, and it will work to be something reasonable. There is a story that I can put along with this. This is actually in those units. You start on the top of a building 64 feet tall. You throw the ball upward into the air at a speed of 4 feet per second, and you let it fall, fly up into the air and then fall down the face of the building to eventually land on the ground. I think that at 5 seconds we end up in the negative, which means that it fell right through the ground and kept going to the center of the earth. But I mean, that's okay. We can dig a hole in the parking lot and just let the ball keep falling. Not a problem. In any event, see what you can do with that one, and I'll see you in the next video.